unexpected geometry video, which I just started making when the batteries ran out. Found this kind of cool video of a rocket launch, whose name you can see down here. Oh man, that's embarrassing. Look at that. Fisheye distortion on my camera. And if you want to look it up, there's its address. This is from early in the launch with a side-facing camera, and that is a pretty flat horizon, but it's kind of hidden by clouds to some extent, and it's kind of hazy because it's still low down. When you get higher up, you've got this, and that's a curve. If I go back a bit and play, you can see it wobbling up and down, and I just demonstrated with my camera's wide angle mode. If you do that with a fisheye lens, the apparent curvature on the screen changes. That rocket has just about reached the limit of its height actually at that point. That squealing sound is unhappy machinery. Yeah. It's still pretty awesome to see the view from up there. And that is the vibration from the gunshot that deployed that nose cone with the parachute. Yeah, this thing actually had a gun built into it to launch, there you go, the parachute. But in the comments, in amongst all the people complaining about it being a fisheye lens, see, this is what a fisheye lens does. And if you can't see the horizon doing that from the side view camera, it's not fisheyeing. This guy says, this guy, I think that's the guy, says you couldn't see any curvature. Well, I thought you could, but it wasn't very visible, because 37 kilometers isn't all that far up. So I started typing a reply, and I thought, I should work this out. At which point oh, this is good. You know what I didn't do? I didn't screw that onto the bottom of the camera. Can't really mount it on the tripod without a tripod mount on the bottom of the camera. Yes, this has all been very well planned. This is an improvised video. This tripod mount has a little button on it with no discernible purpose that sometimes makes screwing it on a bit of a bugger. Sorry, a bit of a bother, I should say. Right, here we go. At least, impromptu or not, I'm not going to include my socks in it this time because I'm not actually wearing any. Little fact you did not need to know. Right, so this is how far I got through drawing it. Curvature of the Earth. That circle is from a quick question. If I draw that circle as the Earth, and you want to know why water doesn't fall off the bottom of it, first tell me which is the bottom. Is that the bottom, because it's at the bottom of the screen? Is that the bottom, because I drew it nearest me? Or is it a trick question and the bottom's here? No, it's a trick question and actually the bottom is here, because, well, the bottom is there, right in the middle, because that is the direction in which down points. Anyway, curvature of the Earth, equatorial radius of the Earth, 6,378,137 metres. And he said 37,000 metres above. So we know the distance from the centre to here. Let's call this C for camera. There we go. In fact, I'll call it C for camera that way around so you can read it. Because I like to make things easy. Also 6378137 here. This is assuming you're above the equator and looking along it. It's just, I mean, you can work it out for any radius you like. It doesn't change that much from the pole to the equator. Adding those two together, 6378137 plus 37000 gives you 64005. I can read my own writing. 137. And Pythagoras' theorem, because this is a right angle, if you are looking exactly at the horizon, you're looking flat across the horizon. So from the point of view of an observer at B, laying on the ground and looking this way, you're exactly horizontal from him or her. So we know this is a right angled triangle, and we know that that squared plus that squared equals that squared. So that squared minus that squared is a very big number, the square root of which is 587.5 kilometres. It's a bloody long way to be looking at a horizon. You can also work out this angle, and I did do the squares on the computer because I can't be bothered working out square roots, you know, 6-figure square roots by hand. I'm certainly not going to go and dig out my sine tables to work out this one. We've got the opposite calculated, we've got the adjacent from NASA, we've got the hypotenuse, number from NASA plus the number from his comment. The angle has a tangent of that over that, a sine of that over that, and a cosine of that over that. As I've got that one already in the calculator, I'm going to divide it by that, inverse sine, and get that angle. That number divided by 6378137 is inverse sine 5.285 is in degrees, isn't it? Yes, it's in degrees. Sometimes it's in radians. 5.285 degrees. There and there. This is a miniature of that triangle. If you want to know how far that is and how far that is, you can do it by scaling down. Or, you know that angle, you know the hypotenuse. Hypotenuse times the cosine of that is this distance. Hypotenuse times the sine of that is this distance. Now the question was, should you see curvature? Oh boy. Looking at the horizon. Do I need those distances? Well, I mean, you should see curvature if the curvature is enough to be visible. The question is, how much curvature should there be? And you're looking at a flat circle. Because your horizon is a set of points equidistant from this point buried deep in the planet here. Just out of interest, how deep? Take the sine of that again. Back to our ratio, and multiply it by 587493. Should be keeping the decimal points to keep it accurate, but whatever. 54114. .54 kilometres down. You're only 37 kilometres up, so this bit here is 17.114. Yeah, I put my numbers different ways up just to really annoy people who are into getting diagrams right. So we know it's 17 kilometres down. There is an imaginary point within the Earth, and a set of points equidistant from that, here, and down there and back up here, is your horizon. How much curvature should you see? Oh boy. Well, in theory, if I made the centre of this exactly under the camera and rotated the camera around in a circle, it would stay exactly in place, but you would see the curve. That is curved on the screen, isn't it? And even if I pull it out here and tilt the camera level, you'll still see a little bit of curvature. Because while the angle from there down to here remains constant, the angle from there down to there is slightly more, isn't it? We're looking at that angle. There's a good measure of the curvature. The angle subtended at the eye by a thing 17.114 kilometres away, tilted 17.114 metres. Bullshit. God damn it. Metres long, 587.5 kilometres away. Now what I need here is the field of view horizontally. How wide a field of view does their camera have? How would I know? Can I just pick a random number? Can I just pick an arbitrary, like 60-degree field of view? 60 degrees is a handy number because It's exactly a third of 180. And these angles around a circle always add to 180. Circle? Triangle. Christ. Always add to 180. So, it's the external ones that add to 360. Internal ones add to... So we can have a triangle with three 60-degree angles, split it in two to get a 30-degree angle and a right angle, and if each side is 2 in length, the two halves of the base are 1 in length. I should really get this your way up, shouldn't I? Which tells us that that is root 3 long. The tangent of 30 degrees is 1 over root 3. The sine of 30 degrees is 1 over 2. Cosine of 30 is root 3 over 2. The tangent of 60 degrees is root 3. The sine of 60 degrees is root 3 over 2, and the tangent of 60 degrees, sorry, the cosine of 60 degrees is a half. Which is bugger all use in this question, but a 60-degree triangle would give us a circle of horizon like that. And I could tell you that instead of 2, it would be 587,493. The question is, how much difference is there in angle between there and there? It's going to be the same down angle, but if you're facing it, if you're facing that way, the down angle is relative to that plane rather than that plane. The same plane. Yeah, if I draw that from the side, which I just did, you have a, imagine this is a flat sheet down here. The furthest point this way around the horizon you can see is somewhere there, which is down kind of this angle. I think that angle will be the measure of visible curvature. Imagine a point from how far around the horizon you can see left to how far around the horizon you can see right. This is going to be above them by an angle. The distance on your screen is its angular size, which is in here. Oh boy. If you're looking down there, it's been a while, alright? I know at that angle, where are they? Well, if that's 2 and that's root 3, that distance is root 3 over 2 is the fraction of how far away it is. So root 3 over 2 times 587,493 is 508,784. Near enough. But that's the straight line distance. Is that really what? No. Bollocks. Let me try that again. Right back to the bloody start, because I need this number, not this number, to work out how far away it is. It's the same distance down, different. Actually, no, because that won't be scaling with the cosine. Right, let me try again. 6378137 over 6405137 is oh, that's, no. Crap. Wrong button. 5.263. Huh. Must have been a typo. Very minor typo somewhere. 5.263 degrees. Not going to make a huge difference to anything. Right. 5.263 degrees. Cosine, go back to the bloody cosine of that. Times, open bracket, 6387, 6378, not 6387, maybe that was the mistake. 37 squared plus 6405, 137 squared, close brackets, square root, equals 9 frickin' million? No, it's times when you know you got something wrong. In fact, there's just no way those numbers came out right. 6, 3, 8, 7, 7, 8. So when did this start going wrong? Squared plus 6405, 137 squared equals square root. Ah, I know what I got wrong. Easy mistake to make. 137 squared minus 6378 137 squared equals square root 587493. Right, gotcha. Let me just write in 0.3174. It's an easy way to keep track of the decimals. Right. That. .2627 degrees, yes. Cosine of that times 587493.3174. .3174. Yay. Is 585016.818. To the nearest millimetre, which is the whole way across there, and this shorter distance to the points on the horizon at the edges of a 60-degree field of view is that times root 3 over 2. .506,639.426. Four. I can spell 4. 506,639.426. Okay. I've got two different down angles. They're both relative to 54114. So down angle to there is that divided by that. Sorry, has a tangent of that divided by that. So in tan is 6.0966 degrees. 6097. What was that? 26, 29 or something? Yeah. Approximately then. It's 5.283. 0.813 degrees different. That's slightly 814, thank you. Sorry, rounding error. 0.814 degrees difference, which if you have a perfectly square view, 60-degree field of view, how many times does that go into 60? How many times does 60 go into that is the better question. Sixty into that, obviously 0 into 0 and 0 into 8. 60 into 81 is 1. So 21 remaining becomes 214, so it'll be 3, which is 180, leaving 34 remaining. 340 is 60 times 5 with 40 remaining, which is 2/3, so 6667. 0.1356667. Sorry, 0.01357. Screw it. If your vertical resolution is 1080, well, let's just call it 1000 pixels. Call it 2000 pixel vertical resolution is double that, you know. 1000, 10, 100, 1000, and double it, you get, well, 66666 doubled is 33333, isn't it? Okay, put a 4 in. Let's be honest, we know it was infinite sixes. 333, off into eternity. And 1 to carry. Double 5 is a 0, so 1 with 1 to carry is 7. 35 times 2, 70. Difficult. 2, and the decimal point has bounced to there. So you'll be looking at 27 pixels out of a 2000 vertical resolution of bulge in the centre of your view. Not bad for 25 minutes.